All right, jumping into another question from the central limit theorem. So the idea of this second one is the contents of a soft drink can is normally distributed, soft drink cans, so multiple, they're normally distributed with a mean of 378 mil and a standard deviation of 7.2 mil. So find the likelihood that an individual can contains less than 375 mil. So this first one, we're looking at, let me just roll in here. So let's just stipulate, or let's get our pen out. So we've got X is normally distributed and we've got our mean here is 378 mils and our standard deviation is 7.2 mil. And remember, we write this as variance, so it's standard deviation squared. So that's how we stipulate the distribution. So this first bit's quite simple. This is back in continuous random variables. We've got our normal distribution. So we're just looking at the probability that the can contains less than 375. So we're looking at the probability that X is less than 375, which means we're going to be doing an NCD, so a normal cumulative distribution. We're looking at 1 times 10 to the 99. So I just do that to make it a really big negative number. And then we're looking at 375. And then you've got to remember on the Casio, so I'm on a Casio here, we flip these around, so we put our standard deviation in there and then our mean in last. So in this just option, we're looking at stats, distribution, normal, NCD, and then I put my values in, 1 times 10 to the 99. We're looking at 375. Let me get another comma, and then what do we got? 7.2 is our standard deviation, and 378. So I get that as a probability. That gives us an approximate probability of 0.338. All right, so you've got about a 33% chance of getting a can that is under that value. So we could draw the distribution if we want, but it doesn't really add anything to it. So that's not even the central limit theorem. We're now looking at our next question that says a box of 36 cans has average contents less than 3. So we're looking at the probability that a box of 36 cans has an average content less than 375. So we should straight off the bat be looking at, well, that's going to be a mean, like we're adding the 36 cans up and we're taking the average of those. So we're looking at, on average, are we expecting the cans to be under 375? And we had here that pretty much we could expect, if we're picking a can at random, that we'd have 33%. So anyway, this here, we got 36 trials. So this is going to be a normal distribution itself. And now we've got to set up our values here. So the mean will be the same as our other distribution. So 378 mil would be that. And now we've got our standard deviation. And this is going to be variance squared. So I might just put our standard deviation here as well, just so we've got it stipulated. Because remember, we're going to be doing this. The standard deviation of this is the standard deviation of our x variable divided by square root of n. So we're going to have, that will mean that we're looking at our 7.2 over square root of 36, which is going to be equal to 7.2 on 6, because 36 is 6 squared, which gives us, it's going to end up being 1.2 mil. So we'll just put a 1.2 in here. Now, if that was, I'm just double checking that. If I was rounding this, I would use this value, but because it's an exact decimal, I'm just going to use that exact decimal. So now we're looking at, well, the probability that our average here, so if we were doing a distribution of the average from each can, that's what this 36 is showing us. We're looking at that being less than 375. Okay, and that is going to be equal to NCD. So again, a normal cumulative distribution, 1 times 10 to the negative 1 times 10 to the 99 to give us a nice big one. So then 375, and then again we're on the Casio. So I noticed the Casio and the TI are a little bit different here in this space. Now we're going to be putting a 1.2 in for our standard deviation now, and we've still got a mean of 378. And we should notice here that this is going to pull our value right in 1 point. We end up here, this gives me a 0.0062, and it's 0.9, so I'm going to round that to 1 to be 3 significant figures. 3 sig figures, okay? And that means, if you think about this probability, that's 0.6% chance. So I'm gonna actually write this answer out because it's from our text, but I think the answer helps the question make more sense. So we've got there is approximately 0.6% chance of getting a box of 36 cans with average contents less than 375 mil, compared with 33.8% chance of an individual can having contents less than 375 mil. So you've got to remember that with this standard deviation, when you start getting these bigger trials, and this is part of the central limit theorem, is that the standard deviation drops dramatically for this. We see our distribution really goes around the mean. And so by getting a box of 36 cans, chances are, you can end up with a can. If you were picking one can out at random, you've got a 33.8% chances below that mean. But you think about in this box here, you've got 36 here, and we're looking at, well, if we add these all up, so you got to remember, you can turn this off now if you're done. We're done the problem. But this, you got to remember that this xn here is like adding all those values up. And then, what am I doing there? So we're adding all these values up, and you're technically adding up 36 distributions here, and then dividing them. And it's interesting here because we're looking at, even though there's a third of a chance that we get a can that is below that, when we add these all up, these distributions, the way they balance each other out, it actually means that in this box, the chance of you getting getting a box of 36 cans with an average contents less than 375. So that means that we're looking at if you add all the mils up in the can and you divide it by 36, on average you're always going to get, well, not always, 99.4% of the time you're going to have an average of more than 375. So it'd be interesting because if you were interpreting this in terms of a problem, as a manufacturer, you would be a bit embarrassed with this third business. But with this central limit theorem, it's actually really interesting because it actually means that this would probably be acceptable as a rate of failure. You're guaranteeing that if someone gets a box of cans, realistically, on average, if they tip out all the contents of these cans, you would find that they should have more than, let's pretend it's Coke, you would have more than 13.5 litres of Coke in here. And so it doesn't matter that some cans are more full than others, and realistically you would get a third of them under. This would be an acceptable level of risk. Thanks.